am going to do work calculations. So our essential question is, what is work and how do I calculate it? So we're going to start by defining work and do a little activity with that, and then we'll work on some calculations. We'll give you the triangle. You've done these calculations before, so they should be pretty easy for you guys. Okay, so let's start with our notes. So I want you guys to think about, what does work mean? So take a few seconds, pause the video, and write down your definition of work, or what you think work is. Okay, so you've had a couple of seconds to think about work. And I bet you think about homework or working at a job and getting paid, but we want to talk today about the scientific definition or the scientific meaning of work. So to do that, we're going to talk about 3 different things. The textbook definition is that work is a force applied over a certain distance. So the key here is that we're focusing on a force, like in our last chapter, and a distance. So any time we think about work, we want to talk about, was there a force and did it move a certain distance? So there's 3 things that have to happen. The first is that force has to be in the same direction as motion. So if we look at the picture of our guy mowing, he is pushing the mower forward. So his force is going forward. And hopefully the mower is also going to move forward. So if we look at our 2 arrows that are on the picture now, they're pointed in the same direction. If force and distance are in the same direction, work did happen. Now the key here is that there has to be a distance. So the second part of this, if there's no motion, there's no distance to measure, you didn't do work. So think about static friction. We can push against the desk up front. You've seen me push against the desk up front. I can push and push and push and push and push, and I might get tired and my muscles might hurt. But if I never get that desk to move, technically I didn't do any work. Okay, so there has to be some sort of motion or movement. The third part of this is that if you're holding something up, you're not working. There's no motion. Okay, so an example of this might be holding a backpack. Now, if you guys carry around backpacks with lots of books all day, you're probably tired by the end of the day. But technically, you aren't doing any work when you are carrying that backpack through the hallways. So let's look at that. When you hold the backpack, you're pushing it up with your shoulders. So our force arrow would be up. Okay, but when we're walking down the hallway, our motion is in a forward direction. So if we look at our pictures, our force and our motion arrows are in opposite directions, or not opposite directions, but different directions. And so we are not doing work. Now let's think of a different scenario. What if you're walking up the stairs with your backpack? So now your force is up and your motion is up. Then you're doing work. But if we're just walking straight down the hallway while holding up our backpack, no work is being done. Okay. We're going to do a short activity now called Are You Working? So the goal of this is to follow a couple of scenarios and decide if work was being done or not and how you know. Remember, in our definition, we want to focus on force and distance. And so that's what you guys want to focus on when you're answering those questions. So go ahead and pause the video and work on the lab for about 10 minutes. Okay, you should have completed the lab and seen that force and motion are required in order for there to be work done. Now, your arms might be tired from holding those textbooks up, but remember, you weren't doing work unless the textbooks were moving up because you were putting your force to hold them up. Okay. So let's go ahead and calculate. So remember, for each calculation we've done all trimester long, we want an equation, and we really want to focus on units. We have a new unit today. So work is equal to force times distance. W, capital W, is going to be work. And we're going to measure it in joules. So that is a new unit. Joule, joule. And that's a capital J. Our force is going to be in newtons, and that's how we've always measured our force. And then our distance is going to be in meters. So remember, if we measure in centimeters, we would have to use a conversion. So let's try a problem. We're going to set them up how we've done. Now, before we start doing all the math, we want to think about one important thing. Is there something to calculate? Are you doing any work? So the direction of the force must be the same as the direction of motion. If not, we can say the work equals 0 without doing any calculations. So don't do extra work. Always think about that first. Okay, so we want to ask how much work is done when a weightlifter lifts a barbell with a weight of 1,300 newtons, a distance of 1.5 meters. So first thing, was there any work? So the barbell or the weightlifter is pushing up and the barbell is moving up. So I would say yes, work was being done. So now I'm ready to set up my problem. So first, when I read how much work is being done. So I'm looking for work and using our triangle, work equals force times distance. Next, we want to define our variables. So the force was 1,300 newtons. And he moved at a distance of 1.5 meters. Next, we can plug our values in. Grab our calculators. I'll give you guys a second to put that into your calculators. So we have work of 1,950. Remember, our unit for work is joules. Just like with our last chapter, these units don't cancel well, so you're gonna want to memorize those 3 units. Okay, let's try our next problem. How much work is done pushing a car 2 meters if its weight is 3,000 newtons? Okay, so we are pushing the car and it's moving 2 meters. We're pushing against its weight of 3,000 newtons. We gotta push that much to get it to move. So let's go ahead and write our equation. Work equals force times distance. We're going to define our variables. So our force is 3,000 newtons, and our distance is 2 meters. We can put that into our equation. Times 2 meters is 6,000, and then remember our unit is joules. So these are very similar to the problems that you guys have seen before. Remember, you need to have all 4 parts of problem solving to get the full points on these. Now our next question says, how much work is done pushing that same car if it doesn't move? So our key here is that if it doesn't move, our distance is 0. So work is force times distance. What happens